Okay, I don't have the password to log in.
Okay, it's working now. Okay, Stephen.
I can go?
Yes, no, we are ready.
Okay, let me, okay, now it's my turn for technical difficulties because I am not able to share my screen properly, which usually means I need to update Zoom. So what I'm actually going to do is I'm going to drop the link to my slides in the Zoom chat, and I'll get someone else to share their screen. Yeah. So, Carlos, if you could, I dropped a link in the
Yeah,
Zoom chat. Yeah, okay, okay, yeah, just as long as you understand. Yeah. Perfect. Thank you very much. So just to start off with, I'm going to introduce myself. So I think, Carlos, you Google stalked me and found my old UVic webpage. For some years now, though, I've been actually working at the Canadian Astronomy Data Centre, which is part of the Government of Canada, so it's the National Research Council of Canada, which is where I work now, where I'm talking to you from right now. Next slide, please. So this talk's going to be a lot of the context of where we are at and why we made the decisions we made when we decided how to exactly host the LSST at the CDC. So there's going to be a fair number of slides saying, all the parameters that went into the decisions we made, and then at the end of the talk, I'll give the actual, what decisions we made and what the problems we're facing and how we think we're going to solve them. So we'll start with a brief history of the CDC. So we've been around since 1986. You can see the top picture there is us from about 1989 or 1990s. I can't remember exactly, long before I joined. And you can tell by the hairstyles that it was quite some time ago. And you can also tell by the technology they're holding up, because that's a giant laser disc, which is the 100th disc that was physically delivered to the CDC from the Hubble Space Telescope. We were originally set up to host the Hubble Space Telescope data, and then we've expanded our mandate to other observatories, all the Canadian observatories, which includes a few surprises like James Webb and the Hubble, because actually Canada has a very small slice of each of all these projects. Very early on, we also started providing access to catalogs, both ours, sort of standard things like UCAC and various other astrometric catalogs like that, but also user supplied catalogs. And over the years, we've evolved to three main activities: archives, data expertise, which I won't really talk about today, and providing compute facilities. Providing compute facilities, the original vision was that, back in 1986, you'd actually have to fly to Victoria, where we had a bunch of computers, and then process Hubble Space Telescope data, because it was not envisioned that there would be any way that you could transfer that amount of data over the internet. Next slide, please. So let's just start by talking about our archives. Our primary mandate is to archive and distribute data from all the Canadian telescopes, which, as I said, includes James Webb, Hubble Space Telescope, and then NEOSat, which is a smaller near-Earth object searching satellite, among others, and then CFHT, Counterfeit Wide Telescope, JCMT, and Gemini on the ground. It's used as an active data repository, so it's not like when you say archive, some people think, okay, well, that's where data goes to be archived and it's never really touched again. But it's actually sort of very much used in real-time analysis. So last week, for example, data came off CFHT. It was for a project looking at for KBOs, the team needed the answers needed the process data right away. So I pulled the data out of the archive and processed it. And that was data that was sort of hours old. But it's also used as a data archive. So Hubble Space Telescope, our primary mandate is to recycle photons. Hubble photons are an example where data that was taken 30 years ago is still useful. And even for CFHT Megacam, it's been on the telescope for 20 years. The data for 20 years ago is just as valuable as for many applications as the data that was taken yesterday. There's 3 copies of the data. We have one on site on the NRC hardware, but we also have 2 copies on, so it says Alliance Hardware. Alliance here is the Digital Research Alliance of Canada, which is a Canadian institution that provides research data infrastructure to the Canadian academic community. And so it's countrywide with sites at various institutions, various universities around the country, and it provides storage and compute to Canadian researchers. So we have 2 copies on the Alliance hardware, one at UVic here in Victoria, and the other one at Simon Fraser University in Vancouver. Our holdings, we have 1.6 petabytes of data in 300 plus million files, and that data comes from 219 different telescopes and different instruments on those telescopes. And the top panel on the right there in red shows the coverage as of a couple of years ago from where on the sky that data came from. The usage of that data is shown in the panel below it. So each red dot indicates one download. So you can see that people in Brazil have been downloading our data, but mostly it's in Europe and the US, but also Japan and Australia. Everywhere in the world, people download our data. And although we have 1.6 petabytes of data, we actually deliver 5 petabytes of data every year in a typical year. We don't track individual users directly for the most part. Most of our downloads are anonymous, but there's on the order of 10,000 users worldwide. And worldwide it is because it's only 50% of our users are actually Canadian. The vast majority of our users around the world are international. Next slide, please. So one key number from the previous thing was 219 telescopes and instruments. 219 telescopes and instruments, but 1 storage system and 1 metadata system. So our system used to be called AD, which I can't actually remember what it stands for, but it actually dates back to the first black and white slide in a couple of black and white picture a couple of slides ago. And we're just now, after 25 years, moving away from it to a new system called storage inventory, which allows us to transparently store data on multiple sites and have that data have high availability and high redundancy. And then the other key part of the CDC success is 1 metadata system. So it's called COM, the Common Astronomical Observation Model. And the figure at the right there is a UML diagram showing where all the bits and pieces of each image, well, not necessarily images, each image or each spectra or each data cube are stored and therefore can be easily searched for. And so COM2, I actually hate it with intense passion. So it's incredibly complicated. On the other hand, once you put something in COM, it's there. You can always find it. It's very comprehensive, so that all different kinds of data from radio to optical to UV, excuse me, can be searched for and stored in one system, not multiple ones for each archive. And this reduces the effort we're required to manage existing archives, and it also means there's a very low overhead to adjust new archives into our system. And then from the user perspective, it means that you go to one web page with one search tool and you can search for all of our data. Next slide, please. So we don't just store the data, we also allow people to do processing of that data. And this is through a project called Campfire, which has that acronym at the top there. It was in 2 phases. The phase 1 started 15 years ago now, where we had a virtual machine-based system using OpenStack that was provided to us by the Alliance, this Digital Research Alliance of Canada. And that gave users access to virtual machine-based computing. And it also gave access to, we would give people allocations on our, the same infrastructure as we were using to use the archive, but just user controlled, so that people could store the results of their processing and share them with either just keep it to themselves, keep it proprietary, share it with their team, or share it more widely with the astronomical community by making things public. It was moderately successful, I would say. Provided an awful lot of power. I'm still using it, but the learning curve was not great. So a lot of users who could have benefited from it were turned off by the difficulties of excuse me, I still got a bit of a cough. The using the system. So phase 2, so 4 years ago, sorry, a couple of years ago now, we switched to a different system, which is based on containers, and that has proven to be extremely popular. So it offers notebook sessions. So the screenshot there is of someone processing James Webb Space Telescope data using one of our notebooks, or it also provides, next slide, please. A remote desktop session. So what you're seeing is a screenshot of what looks like an old Linux desktop. But if you look closely, you can see that it's actually running in the browser. So you come to the site, you log in, and then you start one of these sessions, and then you have what looks like a desktop, but it's now running on our computers. If you can launch software in different Xterms, and when that happens, you're actually running, it's not running the same computer, it's running on a completely different computer. So you have access to far more resources you could possibly have as a single, if you're just working on one machine. And so you can access to 32 cores, vast quantities of memory machines on our system. The key part of it is, and I've sort of pulled out one of the pull down menus, is it's not, the software that's available is not just stuff that we provide. It's actually, most of the software has been developed by other users, and they can share it with their colleagues, or keep it themselves, or make it public. And what that means is this Astro software pull down menu is quite rich. So there's CASA, which is for ALMA, Gemini, but also LSST, UVic KBOs is a separate thing where it's a bunch of different software, and there's many other packages now. This is the older screenshot, but the key here is that all the software is preloaded and ready to go. It's just a pull down menu to access these different pieces of software. And this has really been the thing that has made it take off, is that you don't have to install your own software, and we don't have to install the own software. Power users help other users. And so uptake of this system has been rapid. So we're up to about 350 users at this point, whereas about this time last year or more, like 150 people using our system. So, and before that, it was the year before that, it was less than 100. So uptake has been extremely rapid. At this point, there about a third of Canadian astronomers use this system on a semi-regular basis. Access to this is not as wide as for the archive usage, because it actually requires a fair amount of resources, and it's currently restricted to Canadian astronomers, but that may change in the future. Next slide, please. So yeah, I was saying, oh, perfect. The key to our success is actually not trying to do everything ourselves. So NRC or the Alliance provide us with the actual hardware, as indicated by the purple pen at the top. The Alliance in particular is actually quite interested in our science platform, so their interest kind of feeds into the next part of it. And then there's us, and then we are not really in the hardware business, but we have a close dialogue with the people providing it to us. But our main thing is providing, building the science platform with the data repository on top of that hardware. And then the astronomy software, again, we have some interest in. So we, because many of us are actually not just data scientists, but we're also astronomers. And so we have some interest in it. And then we also have some interest in the science. But what really happened, the key here is this, I was saying the power users providing the astronomy software and then feeding that to sort of regular users. And that is where our system has really taken off. Next slide, please. So this slide is about the square kilometer array. And why am I talking about this? Well, it's in the last thing, the last bullet point. So the square kilometer array is moving forward. Canada has joined it. And as you probably know, it's a large array, huge array of relatively small radio telescopes sprinkled across South Africa and Australia. And SKA produces a vast quantity of data, so its full data rate is larger than the total internet traffic of the world. Most of that never actually leaves the facility. Now, the CDC has been part of the SKA unofficially for years now, where we've been helping, well, we've been participating in software development in anticipation of what happened just a few months ago, where we have now officially joined the SKA as a full member. And so the CDC will become a regional center, and we'll be hosting 400 petabytes in the next 10 years. And we will also require a proportionate number of cores to process that data in the next 10 years. And we are in the process of sorting out the funding for that. Now, the reason why I'm giving this slide in an LSST talk is because out of that SKA money, we are also planning to use some of that money to do LSST, which is a bit more imminent, as a training set for the SKA. And so that's why we are actually able to do this. There are various other funding possibilities that we're thinking of, but this is a much more satisfactory way of going forward. Next slide, please. So now on to the LSST itself. This is just in case anybody hadn't heard of LSST before, 8-meter telescope, 3.5 degrees field of view, with a multi-band survey planned for the entire southern sky. I mentioned the short exposure times, which of course contributes to the vast quantity of data that we're receiving. Now, and then the other part that's key to the rest of this talk is the releases are initially available only to the LSST community. However, after 2 data releases, the older release has become world public. And the key milestones, these are the ones that sort of keep me up at night, is first light is next year. The first data preview is slightly later next year, and then the full release is the year after that. And so if we're going to be ready, we need to really start working on things now. Next slide, please. And again, so this again, part of the context is not directly related to the CDC, but there's a separate proposal being led by Renee Holchek at the University of Toronto, who is proposing a data platform which is connected to the CDC, but somewhat separate. Reusing a lot of our stuff. But this data platform, if it came through, would not just be for LSST, but it would be also multi-wavelength, in particular, a bunch of SKA pathfinders and SKA data would be processed on it, and multi-messenger. So there's actually a gravitational wave component to this proposal. The LSST part would be focused on alert broker. So that would, which is not part of the CDC's plans, but this would be a separate thing where they're actually looking at the alert stream that comes off LSST. And then there'd be also the equivalent of alert broker, which in radio speak is called a transient marshal. They would look at the transients in the radio universe. So two streams would be combined, and actually would also be combined with the gravitational waves thing. So the idea that this thing would be able to really look at the transient universe and combine these three streams of data into one. So it's not funded yet, but we expect to hit results of that in June or July. Next slide, please. So we explored options for what we could do at the CDC. So the first one is just an IDAC Lite, where it's only the statics guys. That's the object catalog, or actually a subset of the object catalog, and the annual coads. So that's and I put a price tag there, which is probably wrong, possibly by a factor of 2, but that was sort of my initial costing. The other option, which is to have a full copy of the entire LSST archives. That's all the individual images, all the catalogs, and that's what sort of France, the UK are thinking of. Then in between those is sort of what I'm calling an IDAC medium, which is all the images and all the catalogs, sorry, all the coads and all the catalogs, but not the individual images. And the reason for that thinking was we did a survey many years ago. So you probably heard of the US Astro 2020, which is a survey of the community to find out what the vision is going forward for the next decade. Canada did the same exercise, which we called the LRP, Long Range Plan. And then as part of that, a survey was done of the likely LSST users, and most of the science cases are met with an IDAC media. They don't need the individual images, but they do need the full catalogs. So that's what's driving this. Now, an IDAC medium does significantly increase the cost and the complexity of an IDAC because those catalogs are huge, and they are, well, as I'll show later, somewhat out of our comfort zone in terms of catalog size. However, I think that's what Canadians want. That's what we're going to provide. And the other idea that we had, and I'm still not 100% sure it'll work, is that we aim to serve the Canadian community, the proprietary data. Our goal, at least, is to provide a worldwide public release of the data that's public, and become a facility that provides that to the worldwide community. Next slide, please. So our goals are to minimize development effort. That picture, by the way, is a picture of the CDC. I'm talking to you from the building at the lower right there right now, nestled on the top of a very pleasant part of the world, I have to say. We don't want to reinvent the wheel. And the problem, of course, is that there are multiple wheels. So Rubin has a series of a well-established software ecosystem. On the other hand, so do we. And we want to be able to provide Canadian users with access to the same mechanisms to all the different data sets, not just LSST. On the other hand, there may be things that you can only do it if you are thinking in a Rubin kind of way, in an LSST kind of way, to produce, to get the science results out. We also want to minimize operations effort. We don't want to have one system that's just for Rubin and one system that's for everything else. And we prefer to keep things as simple as possible. And we want to keep, as I was saying, maximize interoperability. So we should be able to run software that's provided by other IDACs and other LSST software which may assume certain things about what the infrastructure is being run on. But on the other hand, you should be able to run your software on multiple data sets, not just the LSST. It also needs to interoperate with the Candy Apple alert broker, this thing that I was talking about out of U of T. And it should use, to again maximize interoperability, use virtual observatory standards wherever possible. And then, yeah, so there's existing data sets, and then We're also going to be joining Euclid, or we have joined Euclid and SKA, and then CASTAR, which is a space telescope that Canada is leading. Next slide, please. So the current plan is, as I say, an IDAC medium. So 2.7 petabytes per release. Each of these releases is 2 times larger than our current CDC holdings. And of course, we need to keep 2 or 3 copies. So the current release and then the release that we want to make public. And then possibly keep the one in between as well. So that's a substantial increase of our holdings compared to what we did before. On the other hand, it's much smaller than SKA, so I don't really have any worries that this will be feasible. It'll be ingested into our current storage inventory system and served from our current inventory system, the storage inventory, and the metadata will be stored in this metadata system, COM, so alongside all of our other offerings. Now, the one thing that I've highlighted in red as a possible worry is that we need to develop a detailed transfer mechanism of the data from LSST, from the USDF, US data facility, to the CDC. They're using a system called RUSIO, which was developed by the high energy physics community. We, about 4 or 5 years ago, looked at RUSIO and decided it didn't provide quite enough features that we needed to have for our storage inventory system. And so we developed something in parallel. I think our system is better. However, it does require that we now develop a layer that interacts with both RUSIO and our existing system. We're going to have to do that anyway for SKA, but it's just a thing that we need to think about. Now, as I was saying, the interoperability with other CDC's holdings will be fine if we do it with the storage inventory COM method, but we also need to make the data retrievable by the LSST data butler, which is their storage / metadata system. And so that is going to be a bit of a challenge. I think we're going to actually have to spend a fair amount of cycles making sure that that works. I can think of bad ways to do it fairly easily. But we need to make sure that they perform at a level that makes computation that makes the compute easy for and fast for the people using the system. And then ideally, so as part of the science platform I was talking about before, with the shared containers and the shared software, the other thing that has really made this popular with people is we don't just provide data to them via something you have to download it. We provide it something where there's a giant file system that just looks like a giant file system. It's actually distributed across multiple nodes, but it just looks like a giant POSIX file system. And that has proven to be extremely popular with our users. And so ideally, we would also like to make the LSST data available in that system. And that's going to require possibly an additional copy of the data, which requires additional storage, and also require thinking about how to make sure that that data gets there and is redundant against disk failures. Next slide, please. Okay, for the catalogs, this is going to be, I think, our biggest challenge at this point. So as I said earlier, we're planning to host all the tables, all the catalogs. There's no good picture of a database, so I've just put a table of the data volumes, and they're quite alarming. So it's approximately 10 petabytes of database storage. And our current holding is somewhere on the order of 10 terabytes. So it's a factor of 1,000 larger than what we're currently used to. And so we're really going to have to up our game on this particular front. So the current plan is to use QServe, which is the, we currently run Postgres and Sybase as our database backends. The plan now is to switch to using QServe, which is the Rubin developed system. It's optimized for astronomical queries, so it's 2 times faster than Google BigQuery, which is kind of the industry standard for these large databases for astronomical queries, not everything. And the way it works is it's quite clever. It has a small number of powerful disks, which are called the data czars, which are essentially the head nodes, and they have the indices of all the tables. And then a much larger number of lesser computers, the worker nodes, that contain all the rows of the data, spatially sharded, so that if you're doing a positional query, give you all the stuff around my particular favorite object. You can just go to one computer and get the results back. And then if it's doing a full table scan of the whole system, it allows that to be run in parallel across multiple computers. So it looks quite good, but it does require a fair amount of change on our part. So I've put down some questions there in red that are things that are worrying me. One is, how much extra storage is required? So Ruben's pushing for, you shouldn't just have one copy of everything. You should have multiple copies, because that makes the queries faster. But it's not cheap and at these scales. And so the question arises, how much do we actually spend on that particular thing? We're still working with the QServe development team to find out what the optimal hardware configurations are. So what, in terms of actual computers, how much memory per node, what kind of disks, NVMe versus SSD, what's the optimal situation? Do you want lots of nodes with a small disk space, or what exactly? And so we're putting these questions back into the QServe team at LSST, which brings me to the next question, which is, how do we get the support we need from LSST? They've indicated that they're interested to help us at some level. It's not 100% obvious. They can't really run a help desk because they don't actually have that many people working on it, and those people are stretched fairly thin. And then if it's not directly from LSST, can we form some sort of cohort with other IDACs, including, of course, you guys, to where we can all help each other? So that's, and then, the France and the UK are much larger, and so we should be engaging with them as well to figure out if they can, what assistance they can give us in terms of running that. So the catalog, there's the question of, okay, so standing up the QServe thing instance is one part, but then there's also populating with actual data. It requires a separate operation. So the catalog transfer will happen using Parquet files, but again, we need to install Rusio and run Rusio to get those Parquet files from LSST to the CDC. And then we've just learned that, talking to the QServe people, that you go from Parquet and then you actually have to convert files into another format before ingesting them into QServe. And that loading of the catalog also requires some thought. There's also the question that I've highlighted red again, because I don't know the answer, is do we need to keep the Parquet files around for various machine learning applications where many people don't want to access the data via ADQL or SQL or what have you? They actually prefer to have Parquet files and do interact with those files directly with a Python application. So that's what that is. So QServe is currently our baseline plan, but we are keeping an eye on alternatives to QServe. There's various open source alternatives, and there's also Google BigQuery, although it's pretty expensive. And then the other thing, of course, we need to do is hire at least one more database administrator to help us out with this. Next slide, please. So the interface is also a part of the thing that we're thinking of. Our current plan is to actually continue using our own science platform that we've developed. And we've done this. It's not a question of just not embedded here. We've done sort of a technology survey of all the other science platforms that are out there, including, Ruben's science platform. And various other people have also done this and come to the conclusion that our science platform, with its easy sharing of software and other details in this interface is probably the best in class. And so our current plan is to keep using our science platform. Now, that said, we are also keeping an eye on the developments on the Rubin Science platform. So for many years now, we've actually been working together with the Rubin Science platform, the Rubin software teams, and they've been stealing stuff from us, and we've been stealing stuff back from them. And so it's conceivable that in a few years, the Rubin Science platform will have all the features that we have and more, in which case then we'll just go back to using their system. But at the moment, our system is currently superior to the Rubin Science platform. And then for the data base interface, we will, as I said, the base layer is QServe, developed by LSST, and we'll steal that from them. But the TAP interface that goes on top of that is actually CDC software, which they stole from us many years ago. And they put it on top of QServe, and they put it on top of Google BigQuery. And then the actual thing that the user sees is the Rubin Science platform Firefly interface, and that's the screenshot right there, which is developed by LSST, but they actually stole it from IPAC. And I've been told to stop using the word steal in presentations and use the phrase technology exchange, which sounds a lot more polite. But that's where we're at now. Now, all the above decisions are subject to change as the technology evolves. So I'm telling you what our current thinking is. That's not necessarily going to be the case going forward, as you know, evolution happens. Next slide, please. So this is my last slide, and then here again is a picture of the lovely CDC in the lower right there, with a view over to the downtown Victoria and the mountains beyond. So we plan to serve to host an IDAC medium, which is the co-edited images but not the individual images, but all the database tables. We plan to use a mix of Rubin specific and CDC in-house software, and all this is in the context of the square kilometer array, and so things that we're not just being driven by LSST. We also have to make sure that we're anything we build is still useful for the SKA. This comes with a number of opportunities where Canadians will be able to use LSST and all these other surveys to I hate the word synergy, but that's what it will be. It's, you know, to combine these things to produce something that's bigger than the whole, something that's bigger than the sum of its parts. The public copy, you know, distributing it worldwide is going to be, you know, it's a prestige thing where we are able to showcase the wonderful things we have done to the larger astronomical community. However, the challenges are not small. So the data volumes are a factor of a few above our current holdings. So we will need to expand considerably. And then the database volumes are many orders of magnitude larger than our current holdings. So we're really going to be facing a fairly steep learning curve if we're going to going to achieve success. And then, as I was saying above, we need to merge the LSST specific requirements for this thing to the more general CDC SKA operations. And then I think the biggest worry is that serving the public copy is a sort of open-ended thing, whereas of course you're not just providing the data that people can download or run queries on. You actually also have to provide some sort of compute to the wider astronomical community, and that causes problems where, you know, you have to start policing that a little bit so that people use it as much as they need to, but no more. And so with that, I would like to thank you for giving me the opportunity to speak to you today, and I will take any questions. Thank you.
Okay, thank you, Dr. Stephen, for this very interesting talk. It's an impressive work, and you have a lot of challenges. So we now have time for questions from the audience. Okay, please.
And how to beat me? I was trying to find the hand. Go ahead, Reinaldo.
Hi, okay, thank you. That's a very important and nice talk, Stephen. Thank you very much. So I'd like just to ask you about with respect to the imaging data in particular. Is there in the Canadian data center the use of data technology as data lake for raw data and data cube for the data structures? Are you working on those kind of technologies?
So, well, data link is a technology that you need to have to get access to raw data. I believe we already have it running in some sense. That's what the VO standard you're talking about, right?
Yes, right.
Yeah. So that's running now already for our existing data, I believe.
And also, one note that I have concerning our own data center that is going to be built, anticipating the LSST, there will be, I needed to implement some data lifecycle strategy, foreseeing, for example, deleting older data.
Yes. So our current plan for LSST is we would hold the current release and any public release, and the only question, but not the older ones for sure. And the only question is whether or not we keep the one in between. So there's the let's say a DRN, which is the current release that's proprietary to LSST members, but the DRN -1, I don't think will be used by anybody. I think our current plan, although this is something we really need to think about, we would actually delete that, and then when the public release came along, we would copy it, load it again into our storage system. And it's a trade-off between, but certainly not the older ones. The older ones we are not going to be keeping on site. The idea, for the DRN -1, the question is this is trade-off between bandwidth and storage in terms of what's easier. But for the first time ever, yes, we will be deleting files, which is not normally part of our policy.
Okay, thank you.
Hi, Stephen. First of all, many thanks for coming. And although I've known about CDC for a long, long time, I'm very impressed. I mean, I didn't realize how far the scope of the work, etc., and the future. I mean, you guys are pretty ambitious. I mean, SKA really scares the hell out of me. It's also comforting, huh?
I'm glad LSST is a more manageable chunk. SKA, I would say yes, also scares me.
It's frightening. But anyway, it's also comforting to know that well, first of all, I think we have a lot to learn from you guys. I mean, your experience is extremely valuable, and I hope not to steal, but to tap into it as much as we can. And also, it's kind of comforting to know that your worries are our worries, except in a different scale. But we can talk about that. I have one question. I mean, right now, I mean, we can follow it up a little bit later. But my first question is, do you really think very hard in terms of having everything on premise and not talking about cloud? Or what are your feelings about that?
Right. So when you say cloud, you have to be careful, because do you mean cloud or or commercial cloud? So
yeah, I understand. Yeah.
So
I was thinking commercial cloud, but
right,
can also be a national cloud. Yes.
Yeah, exactly. So national cloud is absolutely for us the way to go. So we've been doing that since 2008 with the national cloud infrastructure, and that for us has been extremely successful experience.
That's using OpenStack like the UK does, right?
Well, so we started with OpenStack, and now we've switched to Kubernetes and a container-based system that has been stood up with us. And the reason why that has been working extremely well is because the people at, so this is the people at UVic as opposed to the CDC. Those people are, like I was saying in the slide with the multicolors, they are not just kind of like, okay, write your check and here's your Kubernetes instance. They're interested in our project, and they are able to provide, well, actually, you would have a lot more success if you use this technology that we know about, because we're very nerdy, geeky people who only think about compute, that you guys might not have thought of. And so they nudge us into directions that we might not have explored otherwise. So that's one advantage. The other advantage, of course, is, it's okay, money flows, money comes from the government, comes through. From the point of view of the Canadian taxpayer, it's a factor of 3 cheaper to have the money go to a national cloud provider rather than go to commercial cloud. So every time we cost it out, it's not just 20% more expensive to go to commercial cloud. It's factors of 3 to 6 to sometimes 10 times more expensive to go to commercial cloud. So Google BigQuery, for example, at the moment is great, but it's a factor of 10 more expensive than to do it using hardware that we control.
Let me ask another question. I mean, in this big issues. I mean, do you interact with the high energy physics people? I mean, is this a nationwide like Europe is doing, like with the SCAPE project?
Yeah, so the SKA is going to turn, previously, before SKA, high energy physics was by far the largest digital research infrastructure project in Canada. With us being somewhere in the number 2, but possibly some bioinformatics stuff being on the comparable scales. SKA now puts us in the lead, for good or bad. We are now going to be the largest. We'll be bigger than the high energy physics people. So we are talking to them, but their use cases are slightly different than what we have. So it's not that we completely ignore them, but it is, when we do talk to them, we end up with answers that, okay, well, that would work for you guys, but that's not going to work for us. So there is a dialogue that's going on. It's not, I think we probably need to talk more, that's now that SKA has always been, up until January, SKA was kind of a nebulous thing that might happen in the future. And so we didn't invest into quite enough effort getting ready for it. Now that SKA is a real thing, we're spending a lot more time talking to the high energy physics people, talking to all the other big data people to learn from them.
My final question this session, we can come back later on, letting people leave if they want to. But CADC reports directly to Research Council, right? I mean, you're not connected to any specific university, right? It's a national facility, right?
That is correct, yeah. So
Okay.
The CDC is part of the Hertzberg Institute of Astrophysics, which is where I'm talking to you right now. It's the larger building. And then that's part of the National Research Council of Canada. So we work closely with astronomers and many at universities, and many of our the people who work here are actually adjunct professors, but we're not associated with any one university. We're a federally funded
Institute.
Institute, exactly.
Okay, I'll let people ask questions. I would like to stay on with Stephen.
I have one question. It's about the Common Archive Observation Model. As you know, it's a requirement for like the DEX, also Tabservers. And like Rubbing, can we still do this? Is your technology?
Oh,
That was my private question, Carlos. Come on.
Yes. So all of CDC stuff is open source. Like LSST, we provided open source. We provide some support, but we don't have infinite amount of time. But COM in particular, we're very happy to share. And because it's almost a VO standard, but not quite. Pat Dowler, who's the person who wrote it, decided to become the benevolent dictator rather than have it submitted to the committee, which
it's good or bad.
It's good or bad, but it's good for us at least, and other. So IPAC in the US and Space Telescope Science Institute are adopting it, and it is seeing some adoption. Every so often, we have the idea of having a CO2 what's called workshop here in Victoria, and we've had a couple of those over the years. And I suspect now that the pandemic's over, we'll be looking at having another one of those in the not too distant future. So that's that thing. The tap service, absolutely, you can steal that as well. That's also open source.
Actually, what does it make so great? I mean, Gregory in our IDEC workshop, he just said wonderful things about the Tabserver. What makes a Tabserver different from the other?
It's having not used the other ones, I don't know. I will say that actually that's not quite true. One of the things is that it's written in Java, and it was really written, again, this is a Pat Dollar thing. It's really written in a way that is quite powerful, so that you can do for any CDC table, we have a lot, some of them are quite large. If you do select star with no constraints, it will start running and it will finish. So that there's no row limits baked into it at all. If it's a streaming query, you can do an a sync tap query that with no row limits, and that will just work. So that's really impressive.
But how do you control that? I mean, you get.
I don't know. We've never had a problem. We've never had resource contention on it.
All right.
And with the sync. Now, I will say that the async part, where it actually has to cache the results, that part does have it's hardware limited. But at the moment where I didn't talk about it, we have there's multiple tap services. One of them is actually a user tap service where users can upload their own tables and share those, use the same private group public system. And that one is on hardware that's currently, well, it should be replaced any day now, but they've been saying that for a year, let's say. And that one sort of, if you do a too large a query, it will fail, or worse, it will provide partial results. But the streaming thing, it just seems to work, and so that's why perhaps Gregory is saying such nice things about it.
All right. Anybody interested in asking questions?
We have a comment on YouTube, Bob Abel. Thank you for that talk. It's great to know that my work on the rubbing RSP will help me to speak SK. Is there any other question? Okay, if there are no more questions, we will now wrap this app. This presentation will be available on our website and on INEA's YouTube channel. Thank you, everyone, for attending, and a special thanks to Dr. Stephen.
Well, thank you for having me.
Carlos, don't close the Zoom, okay? We're going to say, well, and those of the interested staying on, please.
Okay, I will stop the recording. I have to stop to the